sequences in a periodic manner, and is very useful for fast signal processing using FFT. Circular convolution. Circular convolution is a method of combining two sequences in a periodic manner. Unlike a linear convolution, as we all know, the sequences wrap around creating a circular effect in the circular convolution. It is mainly used in digital filters, fast convolution, and spectral analysis.
So this is the basic difference between linear convolution and circular convolution. So in linear convolution, there are non-periodic sequences are used, and in circular convolution, sequences are periodic. In linear convolution, output length is defined by nx plus nx minus 1, and in circular convolution, the output length is defined by n. In linear convolution, there is no wrap-up around, and in circular convolution, there is wrap-up around effect present. In linear convolution is done in time domain, and circular convolution in frequency domain. So linear convolution used for system response, and circular convolution used for fast convolution. In linear convolution slower for long signals, and circular convolution faster using effectively. So this is the formula for circular convolution. In a formula, xn means input sequence, hn means impulse response, and n equals to length of the circular convolution. Mod n which causes index wrap-up around and giving the circular effect. The result y of n is also periodic in period n.
So here are some methods of computation, and we all can see that the first method is the time domain method, in which cyclic shift of one sequence multiple element wise and add the result based for small sequences. And later on, here the frequency domain method. In frequency domain method, the frequency domain method converts the sequence to the frequency domain using FFT. They multiply them and take I of dt to get the result. It is very fast for the long signals.
So here are some applications of circular convolution. Circular convolution is used in digital signal processing for fast computation of convolution. Effective-based filtering reduces computation time in digital filters. Spectral analysis, it helps analyze signals in the frequency domain. Communication systems are basically used in modulation, correlation, and equalization. Image processing, usually in 2D circular convolution for filtering and enhancement. It forms the basis of the fast convolutions algorithm using FFT. So I am going to solve one example of a circular convolution. So let h of x equals to 1, 2, 3, and h of n equals to 4, 5, 6. So we are solving using matrix form. So h of 0, h of 1, h of 2 equals to. We have to write this term in matrix form. 1, 2, 3. We have to multiply h of n matrix. So resultant matrix is So this is the final result of circular convolution.
So this is the mental program for the circular convolution. Here we have taken the input sequence. Let me show you. At first we can see here the x of n, which is nothing but the first input sequence, and here h of n, which is the second sequence or the impulse response, we can say that, and here is the n. It is the length of circular convolution. Usually the maximum length or the sum of the length is -1. For circular convolution, it is usually the same length of x of n or h of n. Here we have used the zero binding sequences. If the h of x and h is not equal in the length, then we use the method zero binding, in which we add the number of zeros to the x or h to get the result same, to make their values as the length same. So we can do that. And here is the compute circular convolution FFT method. These lines are used to mainly do the circular convolution and element by the multiplication in the frequency domain, and at last we need to display the result using this command, and the line which we have to display, we can add here circular convolution result and display y. Here we get the final result of circular convolution, which is 66, 68, 66 and 60. This is the summary of our circular convolution topic. The circular convolution combines the two periodic sequences that we have already learned here. It introduces a wrap around effect, unlike the linear convolution, which is straight and can be computed in time or frequency domain. It is mainly used in FFT. It is generally faster and efficient for the larger signals. When the sequences are large, we use zero padding method, circular convolution,